In my previous video, I had talked about viscosity, for which you will find the link in the top right corner. And I felt like I needed to expand on it a little bit further. So we talked about viscosity and about how it's the uh, fluid's internal resistance to the flow, and that means the internal layers of the fluids, when they interact with each other, they create a resistance or friction, in a way you could call it, internal friction you could call it, to the flow itself, and that is what's viscosity. And then we looked at the mathematical side of it as well, that relates the shearing stress tau to the rate of shearing strain, which was represented by du by dy, and the constant of proportionality here that relates these two um, is denoted by mu. And this mu here is viscosity. It's the absolute viscosity, or the dynamic viscosity, or the viscosity of the fluid. And what this relationship tells you is that the plot, if you were to plot shearing stress tau against the rate of shearing strain here, it should be linear, okay? And the slope would be equal to the viscosity then. So this is what that means, that if you were to draw a linear relationship between these two, then the viscosity would be the slope. And right now, if you were to look at slope is delta y by delta x, and if delta x is equal to 1, then obviously the slope is going to be equal to the viscosity y2 minus y1 in this case, which is not necessarily true for every case, right? Because when you're trying to find out slope, which is represented by m, that is equal to y2 minus y1 divided by x2 minus x1. Okay. And in this case, just for this crude oil, x2 minus x1 is equal to 1. And then obviously the slope is going to be equal to delta y, and that is going to be equal to viscosity. In other cases, though, that may not necessarily be true, because x2 minus x1 may not be equal to 1. Okay. Other than that, the actual value of the viscosity is obviously going to depend on the particular fluid that you're looking at. So if you're looking at crude oil or water or some other fluid, and then for that particular fluid, the viscosity is also going to depend on the temperature as well. Okay, we're going to look at that in a second. Just to review one more thing, fluids for which this relationship holds true, for which the shearing stress tau is linearly related to the rate of shearing strain, those fluids are called Newtonian fluids. Okay, and obviously that's named after Newton. And most fluids, whether you're looking at liquids or gases, they're usually Newtonian fluids. And then obviously what that means is that the fluids for which the shearing stress tau is not linearly related to the rate of shearing strain, which is du by dy, or it's gamma dot. If it's not linearly related to each other, then those are non-Newtonian fluids. And for non-Newtonian fluids, the slope of tau against gamma dot is known as apparent viscosity. And what that means is that if you were looking at, let's say, a non-Newtonian fluid, because it wouldn't follow this straight line, it could be something, let's say, like this. Okay, it could be a curve. So then for this, if you were to look at the slope, let's say here, okay, and if this is 1, then the slope is going to be, instead of viscosity, it's going to be apparent viscosity. And why is it apparent viscosity? Because it's changing at every location, right? So if you were to find out the slope over here, it would be different than the slope over here. So um, that's what's going to be different. Um, for Newtonian fluids, obviously, the apparent viscosity is equal to the absolute viscosity in all cases. Um, so now, if we were to look at non-Newtonian fluids, obviously that's Newtonian fluids would have to be straight lines. Okay, they can't be curved because they have to hold a linear relationship. For non-Newtonian fluids, one of the cases could be that this is the kind of profile that the curve follows. Another case could be that instead of curving across like this, it could increase in this manner. Okay, so for these kind of non-Newtonian fluids, these are called the shear thinning fluids. Okay, these are the shear thinning fluids. And for these fluids, what you have to see here is that the apparent viscosity is going to be decreasing with an increasing shear rate. So as the shear rate is increasing, the apparent viscosity is going to decrease. Why is that? Because obviously the slope is going to be greater. Let's say if I'm looking at a point here, the slope for this, if I was to pass a straight line through this, okay, the slope for this is going to be some particular value, let's say. And what is slope? Slope is basically the ratio of rise to run. Okay, it's how much it's rising, y2 minus 1, y2 minus y1, divided by how much it's running across this, which is x2 minus x1. So the slope is going to be highest the more steeper your, let's say, line is. And because this is the steepest, and then as you go further, let's say I move on to this point, and the line that is going to pass through here is not going to be as steep as the one that is passed through here. That means that the slope is decreasing now. That is what slope defines. It defines the steepness of the curve or the line. And as you keep on moving through this curve, you're going to see that the slope is going to keep on decreasing, right? So as the slope is decreasing, and what is slope when we talk about non-Newtonian fluids? It's the apparent viscosity, mu AP. So for non-Newtonian fluids, as the rate of shearing strain increases, for shear thinning fluids, okay, we're especially talking about the shear thinning fluids right now. The apparent viscosity is going to be decreasing as the rate of shearing strain, the rate of shearing strain increases. And what that means is that the harder a fluid is going to be sheared, the less viscous it's going to become. And the examples of this, you can think about ketchup, or you can think about paint or blood. Those are shear thinning fluids. Or if you were to think about whipped cream that you use on cakes, let's say, when you spray it out through a nozzle, right, it flows out. When you spray it out, it flows out smoothly because the viscosity is low at a higher flow rate. Okay, the apparent viscosity is lower at a higher flow rate. But once the whipped cream is sprayed onto a cake now, okay, and you try to dip your spoon into it, it's not gonna flow, and that's because the viscosity has increased, because the rate of shearing strain is decreasing when you're using the spoon instead of the nozzle spray now. Okay, so that's an example of shear thinning fluids. This other kind of curve, this is for fluids that are known as shear thickening fluids. Okay, and for shear thickening fluid, what's going to happen? The apparent viscosity, when you look at it, the slope is increasing now, right? Slope is increasing for shear thickening fluids. And because of that, what that means is that the apparent viscosity, mu AP, is going to be increasing with the increasing shear rate. So that means that the harder the fluid is going to be sheared, the more viscous it's going to become. And an example of that is cornstarch or corn flour. If you add it up in water, if you've ever done this, you try it yourself. If you add it up in water, and you start stirring it slowly in water. It's suspended in water at first, and once you start stirring it in water slowly, it's gonna start looking a bit milky. But when you start stirring it vigorously, faster, it's gonna feel like a very thick liquid. Okay, and that's because the shear rate, with the increasing shear rate, the viscosity, the apparent viscosity, starts increasing as well. Another example could be quicksand as well. Now we've seen two cases for non-Newtonian fluids. Both shear thinning and shear thickening fluids, remember, are non-Newtonian fluids. They do not follow the linear relationship between shearing stress and the rate of shearing strain. So we've covered the two possibilities that can occur. But a third possibility exists as well, and that possibility is that what if there's a certain limit before which no shear rate starts taking place. It doesn't matter how much you apply, how much shearing stress you apply, you keep on applying that shearing stress, no strain is generated, no strain takes place. Okay, so what that means is that that kind of fluid is actually not a fluid because it's acting or behaving as a solid, because one of the conditions that I talked about previously in one of my videos about the definition of a fluid was that the shearing strain has to take place when a shearing stress is applied. So in that case, what's going to happen is that, let's say you've got this point here, which I'll call, let's say I'll call it tau yield. Okay, this is the yield stress, yield shearing stress, and this is the kind of profile I've got. Okay, so what's going to happen here is that I keep increasing tau, but no strain is taking place until the yield stress, tau yield, is approached. Okay, so until that point is approached, whatever material you have, it's behaving as a solid. But once the yield shear stress is approached, then the shearing strain starts taking place. Then that material flows like a fluid. Okay, so you have some kind of relationship that exists between the shearing stress and rate of shearing strain now after this point, after tau yield. Okay, and a good example of this will be that of mayonnaise, because if you were to, if you've ever tried this, take a slice of bread, put some mayonnaise on it, and it's gonna sit in a pile on the slice of bread, because at that point the shearing strain that is being applied on it is less than the yield stress. Okay, so it's gonna sit in a pile on the slice of bread just like a solid would, because what would a fluid do if you were to pour it onto a bread? It would spread out, right? But it doesn't spread out. It sits in a pile on the slice of bread because tau is less than the yield stress. Okay, and right now it's behaving like a solid. But once you take a knife and you start spreading it out now, what's going to happen? The shear stress is going to increase beyond the yield stress, and now it's going to flow into a smooth layer on the bread and act like a fluid. Okay, So that's another type of behavior that is possible for non-Newtonian fluids. Okay, and these materials, these are called Bingham plastics. Okay, these are called Bingham plastics. So you've got non-Newtonian fluids that are different types, of course, but I've discussed here with you the shear thinning fluids, the shear thickening fluids, and then the Bingham plastics. Okay, the units of viscosity, on the other hand, of mu are Newton second per meter square in SI units. Okay, Newton second per meter square. Or if you were looking at it in primary units, it's going to be, if you're looking at the FLT system, force, length, time system, then the primary units are going to be F T L to the power minus 2. Okay, this represents force. Force equals ma basically. So this represents force, this represents time, and this represents length. Okay. So this is the absolute viscosity, or viscosity, simply. But it's also called dynamic viscosity as well. Then you've got kinematic viscosity, and you use kinematic viscosity because in a lot of places, in a lot of equations, you're going to see that viscosity you're going to find in terms of viscosity as a ratio of viscosity to density. So that was given a name, and that is represented by the symbol nu, and this is called kinematic viscosity. And the units for kinematic viscosity are meter square per second. And you go ahead and look and find out what the primary units are for kinematic viscosity. Okay. Other than that, what you will also see is that if you were to draw a figure in which you've got dynamic viscosity on the y-axis, and you've got temperature on the x-axis, and what you will notice is that viscosity varies as the temperature changes for different fluids, whether they're liquids or gases. And what you will find is that for liquids, the viscosity is going to decrease with an increase in temperature. So as the temperature is going to be increasing, the viscosity you're going to see is going to be decreasing. Okay, so if, let's say this is for water, let's say. Okay, so for oils, obviously the viscosity is going to be higher, and it's going to change, let's say, in a profile like this. Whereas for gases, what's going to happen is that as the temperature increases, the viscosity is going to increase for gases as well. Okay, and then you're going to see a trend line like this for gases, for whether it's air, whether it's hydrogen, stuff like that. Okay, so why does that happen? You have to think about the molecular structure of liquids and gases. I'm just going to give you a hint for you to think about this yourself, that why does this happen? Why is viscosity decreasing for liquids when the temperature is increasing, and why is it increasing for gases with the increasing temperature? Okay, so just like think about the molecular structure of gases, how spaced out the molecules are, and then for liquids, how tight, relatively more tightly packed the molecules are, and based on that, then this change takes place. But I'll leave that up to you. So for gases, obviously, this can be modeled by an equation, this behavior of the viscosity changing as the temperature is changing, and that is modeled by the use of an equation which is called the Sutherland equation, and it's given by mu is equal to C into T, where T is the absolute temperature, to the power 3 by 2 divided by T plus S. Okay, and T represents the absolute temperature, C and S represent empirical constants. Okay, so what that means is that if you knew, let's say, because right now we're talking about gases, so for gases, this is the profile that we're going to look at. So if you knew the viscosity at two temperatures, then you could basically substitute that here and you could find out, because this would be a known quantity, this would be a known quantity, this would be a known quantity. So you've got two unknowns, and then you would have two equations if you knew viscosity at two different temperatures. So you would have two equations, and using those two equations you could find out the value of C and you could find out the value of S, and then you could use that and you could go ahead and model that for by curve fitting, let's say, for an entire array of temperatures. Okay, so this is how you do it for gases. For liquids, you can also use an equation to model viscosity at different temperatures, and that can be done by this equation, which is called the Andrade equation. Okay. E to the power B by T, and again, T here is the temperature, the absolute temperature. B and D are the constants, and again, you could, if you knew viscosity at two different temperatures, you could find out the values for B and D, and then you could go ahead and use curve fitting to find out viscosity at all temperatures. Okay, so this is the Sutherland equation, and this is for gases only. And then you've got the Andrade equation, which is for liquids, to model viscosity for liquids. So I'm just going to go ahead and look at a problem. And you've got, let's say you've got two plates. This is your plate 1, and this is your plate 2. And you've got a Newtonian fluid that is flowing between these two plates, and it has a certain velocity distribution between these two plates. The velocity is highest at the central point and lowest or zero at the plates, and then obviously it varies over the distance. Okay, so you've got this profile that looks something like this, and so this is, let's say, you could also imagine it as a pipe actually, if you were to look at it like that. So you've got this as the center line of the pipe, or the two plates, and then if you were to represent the radius by h, then this would be h, and this would be h as well. Okay, and you're looking at this problem with y fixed at the center line. Okay, so you've got two plates. You've got Newtonian fluid that is flowing between these two plates, and these are two parallel plates. They're fixed, and the velocity variation here, the equation for that is, let's say, given by 3 into v divided by 2. V over here is the mean velocity. Okay, so 1 minus y by h whole square. So you've got this velocity distribution. The velocity over here, this is the velocity profile, the velocity variation is being represented by u, which is the function of y. So as y changes, the velocity changes as well. So for this problem, we already know the velocity distribution that's given to us. V here is the mean velocity. Let's say it's equal to 0.6 meters per second square. Okay. Well, what else is given to us? H is given to us. which is the radius, you could say, and that is 5 millimeters. So you're going to have to convert that into meters. And you also know that the fluid has a certain viscosity, dynamic viscosity you're looking at, and the dynamic viscosity is, let's say, 3 Newton second per meter square. Okay. So this is your problem, and what you need to find out is, first you need to find out the shear stress that is acting on the bottom plate or the bottom wall. So then that means you need to find out the shear stress at the bottom wall. Okay. And the second thing you need to find out is the shear stress at the center line. Okay. So let's call that TC. And then the third thing that you need to find is you need to find out the shearing stress at the upper wall. Okay. So these are the three things that we need to find out. We've got the velocity variation given to us. Most importantly, what is given to us in this question is that the fluid is Newtonian. And for a Newtonian fluid, we already know, because we need to find out the shearing stress, right? So that means we need to think about, okay, what or how is shearing stress related to velocity? And that is the relationship, the linear relationship, tau is equal to mu du by dy, right? So this is something from where we can start. That means I need to apply a derivative on this equation, okay? And how am I going to do that? If I was to apply the derivative on that equation, then du by dy is equal to, if I was to apply it here, so I'm going to have two quantities here. One's going to be this one, because 3v by 2 multiplied by 1 is going to stay the same, and the other is going to be 3v by 2 multiplied by y by h squared minus. Okay, so this one is going to go out, because d by dy is not, this is treated as a constant for it. But on this side, this term has a y in here, so that means this is going to become y squared by h squared. H over here, although you could say that it is the function of y as well, but h is constant. Okay, h is a constant number, so that means I can treat this as a constant, and I can take this out, and the derivative is going to apply onto y squared only, okay, because it's d by dy. So when I apply it on y squared, it's going to become 2y, and 2 is going to get cancelled out with 2, and I'm going to be left with minus from here 3 into v, okay, divided by h squared. And obviously this 2 is here, but because this became the derivative of y squared became 2y, then the 2 got cancelled out with 2, and I was left with only y over here. Okay, so this is du by dy. Right. So for the bottom wall now, what's going to happen? For the bottom wall, you've got y, which is equal to, because now you're looking at it in this direction, so y is equal to minus h, because y is at the center line. Okay, so it's going to be minus h at the bottom wall, and that means I can plug that in here, and du by dy at the bottom wall is going to become, h is going to get cancelled out, so 3v by h, that's going to be du by dy. That means tau at the bottom wall is going to become equal to mu into, from here, du by dy is going to be 3v divided by h. Okay. So now you can just go ahead and plug in the value of h here, the value of viscosity, dynamic viscosity, the value of mean velocity, and you'll find out the shearing stress at the bottom wall. Okay. So I'll leave that to you. Just like that, at the center line, you can also go ahead and find it out, but at center line, what you see is that y is going to be equal to 0 at the center line. And that means du by dy is going to be equal to 0. And because du by dy is equal to 0, that means that the shearing stress at the center line is going to be equal to 0 as well, right? And now I'm going to leave this part C up to you. And what I want you to do is, I want you to make a graph with y on the x-axis and tau on the y-axis. Okay. And so you're going to start with y, which is going to be minus 5 millimeters here, and then it's going to be 0 at the center line, and then it's going to be 5 millimeters at the upper wall or the upper plate. Okay, and you're going to have a certain value here for tau at the bottom wall. Okay, and this is y is equal to minus 5. That's bottom wall, so you're going to have a value here, and then the value over here at y is equal to 0. We already know that tau is 0 over there, so you already know that value is somewhere here. And then I want you to see what the value for tau at the upper wall is going to be and how this profile is going to look for the shearing stress.